A very good evening, everyone. A very warm welcome to MazeX 1.0 workshop number 4. We are excited to have you all here as we kick off this incredible journey into the world of Micromouse robotics. This workshop series is designed not just to teach, but to guide you step by step towards building, competing, and excelling. This event is combined to learn, innovate, and compete through robotics. It's a hands on experience where you'll explore more intelligent systems and develop practical technical skills. Throughout this series, you'll also improve your problem solving abilities while working in a collaborative environment. Overall, MazeX 1.0 is not just about building a robot, it's about gaining real world engineering experience and learning how to think creatively. Moving on, now let's take a moment to introduce our industry expert who will be guiding us today. Moving forward, we are honored to have Mr. Nadil Gunawardane, who is a final year undergraduate in BSc Honours Electronic and Telecommunication Engineering, University of Moratuwa. So to continue our session, I would like to invite Mr. Nadil Gunawardane to share his insights.
Thank you, Velshi, for that wonderful introduction. So, I hope I am audible. Can someone please confirm that?
Yes, you are audible.
Yeah, okay. So, I'll share my screen. So, yeah, hope you can see my presentation. Okay, so, yeah, thank you. Yeah, so today we are going to cover the maze solving algorithms and how to integrate those algorithms in the Micromouse. So for today's content, I will tell you a little bit about what the Micromouse competition is and how to represent a maze. Like the maze is actually a 2D matrix, so I will explain about it, how to represent a maze and how to store a maze in a microcontroller, and also the flood fill algorithm, the algorithm that is vastly used by all the Micromouse. Like about 90% of the teams use flood fill algorithm in their Micromouse. So that's the most popular algorithm in Micromouse competitions nowadays. And then the other algorithms, the wall follow and dice try. I will just give a brief walkthrough through these algorithms and also how to integrate these algorithms in the Micromouse. So, what is a Micromouse actually? So I will I think you already know because this is the fourth workshop that you're in. I actually don't know about the MazeX competition, but the standard competition consists of a 16 by 16 grid. So there are 256, right? 256 cells in this arena. As you can see, so in here, this just have this is a 5 by 5 matrix, so this have 25 cells. So in the actual arena, it is far more complex. It's a 16 by 6 grid, and so in the Micromouse competition, it is fully autonomous. You can touch, you can't control the mouse, being outside of the maze. And also in Micromouse competitions, uh, there are two phases, which are the exploration phase and the speed run. This is mainly done to done because of the competitiveness of the competition. At first, what the mouse is doing is exploration. Just it explores the maze, like it gets the idea where the walls are, like how to navigate through it. Like it saves the map of the maze. It doesn't at the beginning, it doesn't have the map of the environment. That means this maze. In the exploration phase, it maps out the environment and it stores it in its microcontroller. And then after knowing about the environment, like it knows, right now it knows what its environment is and how to navigate. And then it can compute how to navigate the environment. So if it knows the environment and it knows how to navigate and it knows the path, then it can move speed at a great speed. So that's the speed run for. And for mapping the environment, there are sensors used. I think you have learned in the previous workshops about those sensors. We use IR sensors or TOF sensors to identify walls in this maze. So those sensors detect walls and map the environment in real time. Moving on. So maze representation. I previously said that. Give me a moment. Okay. I previously said that like the robot, the Micromouse needs to store the maze, the map of the arena, and after mapping the arena, it needs to calculate the shortest path from start to its goal. So how the robot stores the maze in its microcontroller. So that's what we are going to discuss in here. Yeah, this is the more simplest way that I can teach you like how it stores. So the robot, the Micromouse, actually stores the information. Like the main information that it needs to is where are the balls, right? So in a cell, as you can see in this section, like in this example, the white color shows walls, and these are not walls. I think you can see my point. Yeah, it is this one. Yeah. So these are the walls. So when the robot is in cell, let's get it as R and C. So R represents the row that the Micromouse is in, and C represents the column it is in. So the top, there is a wall at the top, and there is a wall at the left. So the parameters for top and left must be equal to 1, indicating that there are walls. And in the right and the bottom, there are no walls in the covering that cell. So they should be like right is equal to 0 and bottom is equal to 0. So this is just a simple example of how to store the state of a cell. Okay, then for much understanding, let's go through the pseudocode. So actually, this is not much of a pseudocode. This is actually C. And as you can see, we create an object like a struct, like to store the attributes of the cell. That means features of the cell. So for cell, there are top, right, bottom, and left, and visited, like the state visited, whether the Micromouse has visited that cell or not. And top, right, bottom, and left means it gives the meaning of this example. That means if the top is equal to 1, then okay, there is a wall at the top of the cell. And if the right is equal to 0, then okay, there isn't a wall in the right side of the cell. So That's the main idea. And for a 16 by 16 grid, uh, we actually create a 16 by 16 matrix before like everything. So we create a 16 by 16 matrix, null matrix, and then we store the features like where the walls are at in that matrix. So as you can see, when robots detects a wall ahead, then maze row call dot top. This is just an example. So in this example, the robot just sees a wall ahead. That means at the top of the cell. So we need to store the status of that cell like, okay, there is a wall on the top of the cell. So maze row call the in this example, let's just take the row is equal to R and the call is equal to C. So maze C and call maze R and C dot top. The attribute is equal to true. That means we need to store that value as 1, indicating that there is a wall. Okay, and what is this line? Like we just need to store the status of that cell, right? So what about this line? There is another cell, right? So this is the thing. So when we detect a wall on top, okay, not this example, let's just imagine that there isn't a wall on the left hand side, just a wall at the top. So if we detect a wall on top in this cell, actually we need to update the cell above it also. Okay, the cell above it, because okay, let's just say that we store, okay, there is a wall on top of this cell, and we do not store the status of the wall of the cell on top of this cell. That means means row -1, the same column, but the row above it, the cell belonging to the row above it. So we do not update that. Okay, we do not update that. So when we are applying the flood fill algorithm, there arises a conflict. That means when you can you can see where the trouble arises when I teach you about the flood fill algorithm, how to apply it. Actually, the flood fill then it doesn't know that there is a wall. It knows there is a wall with reference to this cell, but it doesn't know there is a wall with reference to the cell above this. In this example, so there is a conflict. So the flood fill fails and it doesn't converge right. So when updating the walls, you need to update you need to mirror that wall. That means walls are shared, right? So this top wall is shared by this cell and the cell above it. And let's just say there is a wall in the left also, like in this example. So then if there is a wall in the left hand side, you need to update the cell R C minus 1. C minus 1 also. There is a wall to the left of the cell R and C. Also, there is a wall right to cell R C minus 1. So you need to always mirror the walls that you detect. So walls are shared. Always update both sides. Otherwise, there will be a lot of conflicts. So this is how the Micromouse stores data about the map. So yeah, that's all about storing the map. Yeah, let's move on to the next slide. Yeah, let's talk about the flood fill algorithm. Yeah, this is the main focus of mine today to teach you how this algorithm works. Actually, it is a very simple algorithm. It is not complex, and you can manually do it. You do not need a computer. But when the complexity arises, that means a 16 by 16 matrix, it is quite a bit difficult. So you need to automate how to solve a maze using the flood field algorithm. So yeah, it's been more. Yes. Okay. So okay. I will just give you a quick overview of what this is. This is like the flood fill algorithm. That means think of it as this is the goal. Okay. So actually, let's just not think about where the Micromouse is starting. Okay. So let's just assume that this is like a tank or something like that that can hold water, and assume that we are pouring water to this cell, right? To the goal cell. Then actually, when filling water, the flood fill means how the water flows away from this goal. So as you can see, at first these cells, the cells numbered 1 fill first, and then the cells numbered 2 fill second. Likewise, the cell numbered 11, water reaches there at last. So that's how, like for a visual representation, that's how flood fill algorithm is. It actually behaves like that. So yeah, let's give it a mathematical foundation, right? So it is easier for you to code. So for the goal cell, the main theory is for the goal cell, we just give the number 0, right? Goal cell is number 0. And then neighbors of the goal cell receive the number 1. Okay. Then you might think, okay, why these cells, the 7, these cells haven't received number 1, right? So they have received number 7. Why is that? So that's because from the goal cell to these cells, there is a wall, right? So you can't go to these cells directly, like from here to here, you can't go directly. You have to go, you have to follow this path to go into this number 7. So that's why they weren't given number 1, because actually there are not neighbors. So for if a cell needs to be a neighbor of another cell, you must have access, like direct access for that cell. So from the goal cell, you only have 2 cells that have direct access. So this and this, just those 2. And then, okay, you have given number 1, right? For those cells, for the immediate neighbors. So 1, 1. And then you must think from that cells, like you must give set the reference as of that cells. So what are the neighbors of these cells? Like this cell, and this cell. So actually, you do not consider the cells that you have visited previously. So you just neglect this cell, the goal cell. And then what you do is, okay, now the number of the cell that I am in right now is number 1, right? So the neighbors of number 1 should get number 2, right? Okay, the neighbors 2 and 2, and you just like, and then you see where I'm going, right? So then you need to move to number 2, and number 2, where are the neighbors? These 2, right? So you give 3 and 3, but there is a point. Okay, so after you have given number 1, 0, 1 and 1, and you give number 2 and 2, okay, you just can't go giving only in this direction. Like, okay, I have given number 1 to this one and this one, and I have given number 2 to this one, and this one, and I'm giving number 3 to this one and this one. No, you can't go like that. So you need to give 0, 1, 1, and you need to give, okay, you have given all the ones, right? You have given away all the ones. Then you are starting to give number 2. Okay, I'm starting to give number 2. Then for giving number 2, I am giving number 2 to neighbors of the neighbors of number 1. So 2, 2, and also you need to give the neighbors of this one also number 2. Okay, that's all the number 2s, right? Okay, then only you can move to number 3. So when moving into number 3, okay, you see there are 1, 2, and 3 2s. Okay, 3 2s, and you need to give all the neighbors of these 2s number 3. Then you are giving number 3 here, and you are giving number 3 here. So these 2 cells are the neighbors of this cell, and you are giving number 3 here also. This 3 is the neighbor of this 2. Likewise, you need to fill the entire grid in that manner. So this is a repetitive process, and this takes quite a time since this is like 1, 2, 3, 4, 5. This is a 5 by 5 matrix. This just have 25 cells, but when we expand this to 16 by 16 matrix, there are 256 cells, and it is a lot hard to do this by hand in that scenario. So yeah, just get the concept by a smaller matrix. Like this works with any kind of a matrix. This is the algorithm that flood fill. This is actually the flood fill algorithm. So yeah. Let's apply this algorithm for the Micromouse. So at first, like in the previous slide, I didn't mention you about a star, right? And other thing is, at first we actually do not know, like the mouse doesn't know where the balls are, right? So it when navigating through the maze only, it recognizes, oh, there is a wall here, there is a wall there, and likewise. So in the run only, it recognizes the walls. So that's the main thing. Like let's first see how this works. So initialize no walls none yet. Okay, so at first let's just take, this is the starting point of the Micromouse, and this is the goal. Like this is the middle that the robot, the mouse needs to navigate. So we do not actually know where are the walls at. So we assume actually there are no walls in the maze at first, right? So if we assume that, okay, there are no walls, let's just apply flood fill there. Okay, so initially we there are no walls, we assume there are no walls. Then we apply 0, we give goal 0 always, and then for the neighboring cells, like these are the neighboring cells. Actually these are not neighboring cells, we are getting the Manhattan distance, and we are not going for 45-degree angles. So let's just not go there. Just let's assume that we are getting the Manhattan distance, and in that sense, these are the neighboring cells of the goal cell. So for the neighboring cells, what we give, if the goal cell is 0, we give number 1. And in this cell, what are the neighboring cells? These are the neighboring cells for 1. These are the neighboring cells, and we give number 2. Likewise, we fill out the entire grid with numbers. So at start, the mice receive mice stores. Okay, these are the values of these cells. Like these are the values of the cells of the maze. Okay, so okay, so actually, if there are no walls, we are just assuming, right? There are actually walls. You can see, right? Like if the robot is here, the robot needs to go, the mice needs to go like in this manner or in this manner. These are the shortest parts that it can go. Like assuming that the mice is not getting 45-degree turns and it can't travel in 45 degrees, just 90-degree turns and 180-degree turns and going straight. So yeah, it just needs to move into the cells like in the reducing manner of the numbers, right? If it is at 4, then it knows like, okay, the next cell that I need to go is 3, like 4, 3. Then if we then when it is in 3, it needs to go to the second cell, and if it is in the second cell, it knows, okay, then now I need to go to cell number 1. So likewise, it knows which path to move on. So either it moves in this path or in this path. That's all up to you. That means you can hard code like we have also built micromouses. Like what we have done is, if you receive like 2 possible or 3 possible paths, give priority to the right path or front path or left path. We just set a priority. So according to the priority we have set, it moves. There are cons for that thing, because if we give priority, like let's assume that we give priority right. So if you give priority right, maybe you can explore the maze faster if the mice goes in the forward direction, not in the right direction. So there are things, but let's just move on with this one. So initially what we do is we apply flood fill algorithm, assuming that there are no walls. Then, as I have told, the mice has selected this path, like not this path, to travel to the goal. But in the process, it discovers, okay, there is a wall at the top of this cell. Now it can't go, right? Like it can't go to the goal because there is a wall. So in the flood fill, in the integration of flood fill algorithm in the Micromouse, when the mouse detects a wall, okay, mouse detects a wall, and if the wall blocks its path from going to the goal, there is an if, right? Like if it detects a wall and that wall blocks the path to the goal, then and only then it applies the flood fill algorithm again. Okay, otherwise it doesn't apply the flood fill algorithm, because let's just assume that the wall was not here, wall was just here. Okay, then that wall doesn't block its path, so it can just go uh, the path that it intended to go in the beginning. So it just, like, it doesn't need to like compute again the flood fill algorithm, actual flood fill. So actually, if the flood fill is calculated, maybe it changes the values of the cells, but it doesn't affect the intended path, like the shortest path that it had calculated previously. So the main theory behind it is, if it detects a wall and that wall blocks its path from going to the goal, only then it recomputes the flood fill. Okay, so okay, it detects a wall, right? Okay, so it just recomputes the flood fill algorithm. 0. Okay, it just initiates 0, and for the neighboring cells it gives 1, and then in this case This cell has received one in the initialization phase, but in this scenario, like it is not a neighboring cell, right? So it didn't assign one to this cell. So the neighboring cells of the goal cells are just this one, and this one. So it assigns number one to these cells only, and then from these cells it looks at, okay, these are the neighboring cells, just these ones. So they assign number two, and moving on to the number two, they assign number three. So the cell that held number one initially turns into number three. So yeah, then mice decides, okay, the flood field was applied again. Now my path changes. The path that I was going to travel changed. So now I am at 3. Then I must move to number 2, right? As of the priority that you have given earlier. So for in this scenario, I have given priority to move right. Okay, so it moves right. So it moves to number 2, and then again it moves to number 1, and then it reaches the goal. So that's how it recomputes the flood field algorithm every time a wall blocks its path. So yeah, this is clearly shown in here. Okay. Okay, let's move on to the algorithm. Like, if you want to take screenshots, please take those screenshots, because this might be important for you to develop your own flood field algorithm. So this is how the flood field algorithm is coded, and you can go through this and how the distances are updated. You can see right here, and yeah, and also the robot move decision, read sensors, recompute all. Like you can go through this code this, and you can develop your own code for solving a maze with flood field algorithm. And actually, the time complexity of this one is O(n) squared. So, like if the cells are growing large, that this n is for like a 16 by 16 matrix. This is the width of the matrix, right? N is equal to 16 by for a 16 by 16 matrix, and n equals to 5 if it is a 5 by 5 matrix. So with the growth of the width of the matrix, this squares the times complexity squares. So, and the space squares. And the thing is, this is a lot of consuming the space, time, processing power of the microcontroller. So flood field algorithm is a bit calculate, like it needs a more of a calculation time, so, and calculation power. So it takes time to recalculate, like recompute the flood field algorithm in a microcontroller. So that's why we use STM32 microcontrollers, which are way more faster than Arduino Nano, Arduino Uno, like those chips. So you can use a TNC microcontroller, which has like a very high clock speed, which is about 80 megahertz, I think. I cannot remember that accurately, but this is much more calculation expensive, this algorithm. So yeah, as I have said earlier, this is used like most of Micromouses. This algorithm is used. Yeah. Yeah, that's about flood field algorithm. I think you have gained knowledge on how to compute flood field algorithm and how to do it for yourself. Like if you I give you a matrix with holes and everything, I think you can compute the fill algorithm for yourself. It is like for me in the beginning, I was afraid about the flat fill algorithm. I I thought I couldn't understand, but when I learned it, it was very simple. It's just it is not a thing to be afraid of. Even school children all of students also can do that. So yeah, that's a very simple algorithm. And moving on to the two phases of the Micromouse run. There are two phases because of the competitiveness of the Micromouse competition. The thing is, you just do not need it is not enough just to solve the maze. You need to solve it fast. So that's why they are you can get many runs in the given time frame, and the run that you have like you have spent the the least time taken run is considered as your best run, and the marks are given to that run. So that's why there are two phases: the exploration phase and the speed run phase. So in the exploration phase, what the robot is doing is actually a robot is mapping the environment. Like it is, as I have said earlier in this presentation also, it maps the environment. It registers where are the walls at, where it registers where the walls at. That's the only thing that it does. And in the speed run, okay, now it knows where the walls are at. Then what it does is it computes the path, and it moves in the shortest possible path that it knows. So for this thing, there is a slight thing in in most of the in some cases the mice doesn't explore the entire maze. So sometimes you need the micromouse needs to go like 2 or 3 runs to explore the entire maze and update all the weights. All the weights means these ones, right? So update all the weights in the matrix, so it knows, okay, this is the shortest possible path that I can go. So yeah, for the flood field algorithm, there is a thing, you need sometimes 2 or 3 runs to explore the entire maze, so it gets the full awareness of the entire maze. So yeah, exploration of the entire maze means the mice, most of the time, mice needs to move to every cell. Yeah, so that's the exploration phase. And after knowing about the full map and updating all the weights of the cells, then it knows what path to take, what is the shortest possible path, and then we can increase the speed of motors, and we can run at the maximum speed of the motors of the Micromouse. So yeah, that's the speed run, and speed run is there to reduce the time that it takes. Okay. Yeah, moving on to other algorithms, I'm just going through explaining about the wall following algorithm. Actually, that algorithm is not used, that it is actually highly not recommended to use this algorithm in these scenarios in the present competitions, because this doesn't solve the maze at all. That's why. And there is Dijkstra's algorithm, and there is the A-Star's algorithm. Yeah. I'm just telling you, there is an algorithm like this, this is no use. This algorithm is no use. This algorithm can't be used to solve this maze. In the present time, in the previous, in the earlier days, the goal was at corners, right? So the robot starts somewhere, and the goal was at corners. So this wall follower method can actually solve those kinds of algorithms. So there is a slight error in this slide. I will tell you about that also. So what the wall follower algorithm means, it just assume you can assume that just assume that you are in a real life maze. Okay, you are in a real life maze, and this is the start, and you are facing this direction. I can, yeah, and you are facing this direction, and you just need to place your left hand on this wall, right? Then what you need to do is you just place your left hand on that wall, touching that wall, and then you have to move forward, right? So touching wall, you cannot get your hand away from that wall. You just you have to touch a wall every time that you are moving. So you just keep moving, placing your left hand on a wall. That's it. That's the algorithm. That's the entire algorithm. So in this scenario, it just moves like this. Moves here and here and sorry, like this, right? Yeah. Yeah. You can see that it doesn't even reach the goal, right? That's the thing. Like it just keeps looping, looping, and looping. And I have seen that some assume that we are using um, left hand or right hand rule. Like I have told you that to place the left hand, you can do the same thing by placing the right hand also. But in the current scenarios, you can't solve because the goal, if the goal was in a corner of the matrix, yeah, definitely you can solve the matrix, right? But because of this reason, the goal was moved into the middle. So that's the thing with the wall following algorithm. Okay. So I won't go through Dijkstra's and ESTA because it takes some more time. I will tell you the application of that Dijkstra's and ESTA. This is actually like in practice. What we use this Dijkstra and ESTA is for computing the shortest possible path when the map is known. Okay, so when the map is known, let's just assume a good example for implementing Dijkstra's and ESTA. Like if we are implementing 45-degree turns in a Micromouse, then we can use Dijkstra's and A-star. Okay, A-star for deciding the optimal path for the Micromouse navigation. So, but for exploration phase, like every time we use the flood field algorithm because for the exploration phase, instead of going the Micromouse in 45-degree angles and 45-degree turns, it is more robust and more accurate for the robot Micromouse. Since it doesn't know about the maze yet, to go in 90 go straight, turn 90 degrees and turn 180 degrees and use flood field algorithm for the initial exploration phase. After the exploration phase, we can use Dijkstra's or A-star algorithm to compute the shortest possible path for reaching the goal with added weights. Like we change the weights for the matrix. With change matrix, we can compute the shortest possible path with 45 degree turns with Dijkstra's and A-star algorithm. So you can find more about those things. I think many students now, like many teams, are integrating 45-degree turns and 45-degree travel. So you can go through the internet on how to implement those things. But as a starting point, just use flood fill algorithm, and just use flood fill algorithm for the exploration and for the speed run. Then after you have mastered it, you can move on to Dijkstra's and Nesta, implementing Dijkstra's and Nesta algorithms also. And moving on, like we have talked about how to implement flood fill algorithm, how to store a maze in the microcontroller. Then I am combining all of them uh, into how to integrate those, like everything that we have talked about this far into the robot. Yes. So as of the flowchart, you can see we take IR and TOF readings. Then from those readings, we can say, okay, there is a wall in the left hand side or front or right door. We detect walls. Okay, we get the sensor readings. We detect walls from those readings, and then we do the flood fill update if and only if the wall that has been detected is blocking our path to the goal, right? Only then, otherwise, your Micromouse will slow down. That's the main thing. Like computing flood fill algorithm, every time that you have detected a wall, that will seriously reduce your speed in the Micromouse. Just update, give the flood fill update when a detected wall is blocking your path. And then after the flood fill update, you can get the move indication, like where to move, like where to turn, if you need to turn to right, if you go to the straight, if you move to left, like you can get the move indication, and that decision is communicated to the motor control. That's the main flow. And as you can see in this code, while it's not at the goal, right? It's not at the goal. You just at first read the sensors. There are sensors in the front, left, and right. I think you have also gone through the hardware setup of the Micromouse in the previous workshops. And then you, after detecting from the sensor, like getting the sensor readings, you update the wall map and then recompute the flood fill algorithm, picking the best neighbor. Like best neighbor is picked by what is my current value, and current value my, like which neighbor has current value -1 value. Okay, and then moving to that neighbor and updating its version. That's the thing that we are doing from this. Like that's the only thing that we need to do in the sense of integrating flood fill algorithm, like the main algorithm for navigating and exploring the maze. Yes. And then these are just command box and how to fix them. Some instances, there are more instances than this. I just listed out some of those instances. So if the robot spins in circles, you have literally forgot to update both sides of a wall, as I have mentioned in my previous slides. If you detect a wall, you need to mirror that update. Okay, and then robot goes through walls. That is also sensor thresholds are too loose, or you haven't detected a wall correctly, you haven't updated that one, and flood fill never finishes. Sometimes, actually, there there can be errors in a maze. Okay, right? So in a competition that I went with my team, actually the maze was unsolvable. So in that kind of a scenario, Floodfield will never be finished, and uh, uh, actually the organizers of that event changed the maze afterwards, and then speedrun hits the wall, so that might occur because of the errors of the map. So this just narrows down to mapping errors, not detecting walls, those kinds of things, and localization of the robot. That means if it doesn't know the cell that it is in now currently, then also there will be a lot of errors. Like if it doesn't know where it's at, then it can't navigate. So yeah. Okay. I think I do not know whether you have a paper or not, but I think I will just do this example with you. If you do have a paper, just please try to do this one, this exercise. I think it is better for you to learn how to do this. I won't give 5 minutes, but let's just go through, right? Uh, yes. So this is the answer for this scenario. If this is like you can assume why these are infinite, right? Why these are infinity? This is because if the robot is in any of these squares, it can't reach the goal, right? Because the walls are surrounding these areas. So this goes into infinity, and this is also goes into infinity. Yeah. So that's the thing. And as you can see, the same theory applies here. This is the goal, it is 0. And this is the neighboring cell, it is 1. And what are the neighboring cells of this cell 1? They are these two are the neighboring cells, and you assign number 2 for those cells also. And yeah, the loop continues. That's it. And I'm just adding a scenario. Okay. So as you can see, what if I add the wall here? I add a wall here. How the recomputation of the flood field algorithm changes? So add a wall here. Okay. Then only, as you can see, only these cells gets updated. These, and this. Like I haven't just, there is no formula, like there is no method for knowing like, okay, only these cells are going to get updated. I just applied front fill again. Like it is no brainer that these cells are not getting updated, right? Actually, these cells are not getting updated because you add a wall here. That's just obvious. Just reapply flood fill algorithm. That's the only thing. And by reapplying flood fill algorithm, you can see only these cells are being updated. And then, okay, the robot detects it can't go straight forward. As of the previous scenario, it can't go straight. Then, what is the path that it now gonna take? It is this path, right? It is just this path. So yeah, that's very easy. Okay, I think you got that example also. Yeah, those are the things that I've intended to cover in today's session. So, representing the maze as a 2D grid of cells and flood fill algorithm, it's actually a breadth first search, and also how the exploration happens at first, like the mapping of the arena, and how the speed run occurs in the second phase. And always mirror your updates when you detect a wall. Mirror the update of that, like you have detected a wall in the right, then you have to update that wall on the left also. And wall follower doesn't work. Just don't apply that one. Yeah, those are the things that I've intended to cover. Yeah, thank you so much. If you have any questions, please ask now. I think there is a link that you can post questions. So yeah, I'm open to Q&A now. Thank you so much.
Thank you for that insightful session, Mr. Nadil Gunawardane. You can ask your questions by simply scanning the QR code displayed on your screen. This will directly take you to a Slido where you can submit your questions in real time.
Okay. There is a question at the start of a competition when initializing the. How do you know the ending point of the maze? Yeah, that's actually a good question. Uh, Actually, they give us the ending point. So in the maze, in competitions, they always give us the ending point. In a 16 by 16 matrix, it is the four cells at the mid. Most of the time, yeah, it's the four cells at the mid of the maze. So only thing that changes are the balls of that cell. Yeah, that's a good question actually. That was also a question that I had in my mind, like when learning the flood field algorithm. You just need to know, right, where the ending point is. So they give us the ending point. In every competition, they give that. Yeah, definitely they give that. Otherwise, you like you cannot apply flood field algorithm. You need to know where you need to go, right? So yeah, they give that. Okay, and when using sensors to detect the maze, how the line keeping algorithm is executed simultaneously while the flood fill algorithm is running. Yeah, mm, you can do it uh, in several ways. Like you can actually do it sequentially also. Like actually. You just don't need to do those two things simultaneously. Uh, Flood fill algorithm is only applied when you have detected the wall, right? Until then, you can navigate in the maze by using your sensors, and then after you have detected a wall, then actually the navigation by using those sensors ends, right? So after that, you can stop navigating using sensors and just run flood fill algorithm. And also, you can implement RTOS in Micromouse computer, like in a microcontroller. So I don't know whether you know about RTOS. It is known as real-time operating system. So you can run multiple tasks parallelly. So you can run motors, sensors, and the flood fill algorithm in parallel kind of threads in a computer. Yeah, that's the answer for that one. Can we do all that in a very short loop time in a microcontroller like Arduino? That's a slight problem that uh, we get. We actually do not use Arduino in Micromouse competitions because flood fill algorithm is using much more computational power, and in an Arduino, it takes time to calculate a 16 by 16 matrix. We actually do not use Arduino. It is better if you can use like ESP32 controllers. ESP32 is also a good microcontroller, and also a DNC and an STM32 also. Do we have multi-threading like thing in microcontrollers, because we are coding in C++ like in Java? You mentioned RTOS. Is there a mechanism to multi-thread? Yeah, RTOS is like multi-threading, but it is actually not multi-threading. It is like you are giving priority to tasks. Like let's assume that I will describe you to getting an example. Like you need to blink an LED. Like you have 3 LEDs. You need to blink an LED at 10. One LED at 10 hertz, another at 20 hertz, and another at 5 hertz, right? So you can blink all those 3 in a sequential code also, but you can use RTOS. So it is like multi-threading. Yeah, you can learn about RTOS. It is not complicated. Like there is open source free RTOS. Yeah, you can go through that. Like you have an entire tutorial in YouTube for RTOS implementation in STM32. Yeah, thank you so much. If you have any more questions, please ask. Like how the arrangement of sensors needs to be. Why are we using encoders also? Can you give some resources for RTOS and give a basic intro about that? Giving a basic intro about RTOS takes some much time. Like that's the basic intro that I can give you about RTOS. That means it is kind of multi-threading. Like it is used to run multiple tasks simultaneously in a microcontroller. That's the thing. Like I cannot dive deep into them because with the time that I have, like it's quite a subject. I will share some things. Let me see. Um, I think this playlist I don't know. Is this a playlist? Okay. I think this has a playlist. This is just video part 1. This is implementation of RTOS in ESP32. Oh, yeah, like you can get an idea about RTOS. I will share this one. Yeah, just use this as a starting point. Okay. I have shared that one. Start. Can you share the screen of the questions, please, the organizers? I think it is easy for me. Yeah, thank you so much. I have pasted that YouTube link. So just like DigiKey has a lot of resources for artists. Like they have a tutorial. So yeah, just please go with that. When I searching about that, I found that it was used to store reading the reads. So reading records we can use. I do not get that. think reinvented the yeah, you do not need to like implement RTOS from the beginning. There, like you can use free RTOS. That's what I have told. Like it's an open source RTOS software. Like you can directly implement. You have you don't need to implement RTOS. Uh, free RTOS. I'll paste this link also. Why there is something called RTOS. I have pasted the link for free RTOS. Just go through that one. Why there is something called RTOS. Uh, like, why are you asking that question? I mean, I didn't get that one. RTOS means like, as I understand this question, uh, like in microcontrollers, and also in like general computers, also you need to run some processes parallel, right? So, like for getting the encoder readings, like people that have worked with encoders know that you cannot like miss an encoder step, right? No, I mean, why there is something like that? What is the purpose of? Yeah. That's what I'm talking about. So, like, like people have worked with encoders know that in encoders you can't miss a step. Okay, so if you miss a step, your whole calculation go wrong. So in STM32, there is a separate register for storing the encoder values. Okay, because of that, we can just give a message to the like register, give me the encoder value right now, and then get. But microcontrollers that do not have a dedicated register like that, you need to use interrupts, kind of a thing, right? Interrupts means every time you hit a like hit an encoder encoder step, every time you hit an encoder step, you need to register that value. Like, okay, you need to store that value. Okay, the encoder step needs to be incremented by +1, +1, +1. You need to keep that count. Like we use interrupts because we need to interrupt the code that we are running to step. Otherwise, we would miss that step. So RTOS is there actually for handling those kinds of things. Like if you are using RTOS, those two functions, like the main code, like let's assume that okay, you are running getting sensor data from uh, uh, getting sensor data and the encoder data parallel. So you need to run those two events parallel. So RTOS is there like uh, for achieving that kind of an ability, that kind of a function in microcontrollers. Uh, I think that's the best explanation that I can give. Uh, Run two things, three things, or like multiple things parallelly in microcontrollers. We use RTOS. That's a single line that I can give. What is the purpose of using RTOS for running multiple functions? I think I have given us. Can we use RTOS in any STM? Yeah, probably. I think so. Like, yeah, RTOS is enabled. Not enabled. I mean, we can run RTOS. Yes, yeah, yeah, right. Go anyway. Yeah, in any STM32 microcontroller, you can run RTOS, ARM Cortex, free RTOS, or Azure RTOS. Yeah, you can run. Actually, I highly recommend using RTOS in developing Micromouse because it just reduces bugs. So other than running the entire code block and running entire getting sensor readings, getting encoder readings, and computing flood flow, all those things in just one code. You can use RTOS like to run things parallel. It's way to write code more efficiently. I mean, maintainably using double OP with separate codes for each functionality without long code. Yeah, yeah, definitely. The experience that I have is with developing our Micromouse with this Team 32. So for the functionalities, like actually for breaking down work among our team members, we developed separate, like one looked at how to calibrate sensors, how to get the sensor readings, and how to update walls from those sensor readings. And I looked mainly at the controllers, like getting those sensor readings and how the robot is going to go straight, how to get a 90-degree angle perfect, like accurately, and how to get a 190-degree angle accurately, and how to align the robot itself with the wall. Yeah, those kinds of things. So we maintain separate files for those things. Okay. Is CubeID has that option? I have notes. Yeah, yeah, definitely CubeID has that option. You can use double OP because you can code with both C++ and C in CubeID. So in our scenario, we have coded in C++ the flood fail algorithm and all the other controls. That means getting sensor data and getting encoder readings and giving motor commands. All those things in C. Yeah, so you can like make libraries like kind of thing in C, and you can import everything in the main C++ code. So yeah, you can do that in CubeID. And also write code more efficiently. That means for each functionality, you can develop kind of a library. For getting sensor data, you can call, okay, sensor.left, yeah, like get data, sensor.left, like if that function is called, you can get the sensor data. Likewise, you can maintain separate files for each functionality. So, and it is way more easier for your team also to develop functionalities. Package like structure in Java. Actually, I have no experience much with Java. First of all, I do not recall, like, I cannot answer that in terms of Java, but the thing is, with my expertise in C++ and C, what I know is you can create like libraries .h files and import them in the main C++ code. So that's the thing that we are going for, we are using. Not much package, like we develop kind of libraries for those things. I actually don't know much about Java. Like they are just actually simple things. It's not much a thing to worry about. Like there is a source folder, there is an include folder. Uh, when the project is created in the KubeID, those folders are already there. So there is a main file, main.cpp file that you can run, and yeah, there is a main.cpp or C file, and in there you can create the library files, the codes, and in the include folder you can put the header files for those libraries. I think like one who knows C and C++ knows what I'm talking about. Like it is not a hard, I don't know, but for embedded system development, it is not much of a hard language. You just can go through, if you already know a programming language, you can go through C and C++, just the terminologies are different. Yeah, do you recommend platform? Yeah, absolutely. I definitely recommend platform IO. Like actually, do not use Arduino IDE. Uh, it is okay. Like platform IO is like well built extension in VS Code. Just use that. I actually, if I like, sometimes I use ESP32 and Arduino still. Uh, but for those things, I do not use uh, Arduino IDE. No. Platform IO is far more better because I can get recommendations. I can integrate my Copilot and everything also with that, and it eases my coding and it eases debugging. So yeah, just use Platform IO. So if you guys do have any more questions, okay, what is the best STM that you recommend for Micromouse? There is there isn't a thing called best one. Like STM32 boards are black pill. I haven't used black pill. I have used just blue pill. Like with blue pill also, it works totally fine. I mean, otherwise, we have used F4, F405. Yeah. 405 or 407, I think. We have used, I think, as I can remember, we have used STM32 F series microcontroller. If I have, let me show you. Just give me a moment. Actually, Mali, I don't know about the black pill. I just use blue pill. But black pill also does the work. Wait a minute. Yeah, sorry. This is the Micromouse that we have built. So I cannot actually see right now what we have used. But I can surely remember that we have used STM32 F series board F4 or 5 of, yeah, 405 or 407. I cannot uh, remember which one we have used. Yeah, as you can see, this is Micromouse that we have built. So, yeah. Yeah, just like my recommendation is doesn't like do not much think about what is the best STM board or whatever. Like uh, STM32s are quite fast, so anything like any STM32 will do what you are intended to do. Like if you are planning to like as beginners, I don't know whether you are a beginner or not, but if you are a beginner, just start with an STM32, just a blue pill or whatever. I think blue pill is the least expensive, right? I think I don't know, but just start with that one, blue pill. And if you are going to build a high speed Micromouse over like with the increasing of speed, I sometimes you might need a faster processing one. Yeah. You guys facing problems with finding a good wheel for the robot. There are no good wheels in the market right now. I think. Yeah, we face problems actually. Uh, yeah, we. Uh, I do not recall much, but I think we imported the wheels when we got the uh, encoder motors. Yeah, and also I think we have changed the wheels also. Like we have got some wheels from another team. So yeah, good wheels means we are using we are using encoder. We have used encoder motors which are N220 motors. Uh, and this is the standard wheel that comes to N220 motor. Is a standard wheel, and with this wheel, sometimes these were not in a single plane. Like this wheel was what you say to it, twister like a thing. Like it was not in the same plane, so because of that, the Micromouse wiggles. You need to find a good wheel for that one also. But if you are building a small Micromouse, this is quite a big Micromouse. Uh, you need to go for much smaller wheels, and also you need to use those brushless motors that you use in drones. I think those kinds of things. Those are D-hole rubber wheel. Those were bad in our build. Uh, yeah, like that means what you are using, like what are the motors that you are using, N220 motors, so smaller motors. That depends. Yeah, N220. Yeah. So this is a standard wheel. This is a standard wheel for N220 motors. Why was it bad? Like, what were the issues that you have faced? Like, didn't it fit or what? What are mechanical? They were not precise on turns. Why was that? Mm, I don't think so. That means we built this micros like it was quite precise. I think you need to look at like the gyroscope that you are using or the encoder, getting encoder readings of you, like fusing them, like the sensor part that I think you need to focus on, not the wheels. I think like okay, maybe because of the encoder. Yeah, yeah, definitely like the wheels. you cannot get the exact diameter of a wheel, right? So there are always errors. So you need to implement mechanisms for reducing those errors. Some things, some hardware issues can't be resolved in terms of only hardware. You just need to add some software parts also for reducing those errors. Yeah, you need to resolve those with the sensor readings and stuff. I think that's the issue. I think I have given the solution, like some insight to you. Is that so? Yeah, yeah. We designed the PCB. And we designed the PCB and we ordered it from JLC PCB, and it's a PCB manufacturing plant in China. Like you guys can also do that. That's not a big deal. Thank you so much, Molly. Thank you. Like, if you need to get more information, I will share you like mm, this is a great playlist that actually for building Micromouse. At first, I was overwhelmed, but after going through this video series that I have posted right now, uh, yeah, I posted right now. I think, yeah, I will share this one on the chat also. You can get a clear understanding of how to make a Micromouse and how a Micromouse works and what are the tricks. Like, this series was made by actually a legend in Micromouse. Like, he was in Micromouse from the very beginning. So yeah, uh, you can get a great insight from this video series, and also just search GitHub for Micromouse. There are tons of GitHub repositories for code bases, how they have implemented the sensors, why are the sensors in that manner, those kinds of things. Yeah. Yeah, that's pretty much it from my side. If you guys have any more questions, please ask. Okay, I think that was pretty much it. Yeah, I think so.
So now we would like to present this token of appreciation to Mr. Nadil Gunawardane in recognition of his valuable contribution today as a guest speaker at MazeX 1.0 workshop number 4. Your insights, knowledge, and time have truly inspired and guided all of us here today. On behalf of everyone, we would truly appreciate your time, effort, and valuable knowledge shared with us today. So, before we wrap up, We'd love to capture this moment with all of you. Could everyone please turn on your cameras and switch on your virtual backgrounds for the group photo? We'll give you a few seconds to get ready. Okay, let's take a snapshot at the count of 3. 1, 2, and 3. Thank you. So, moving on, as we come to the end of today's workshop, we would like to thank each and every one of you for being a part of this journey. This marks the conclusion of our workshop series for MazeX 1.0. We hope the knowledge, skills, and experiences you gained throughout these sessions will help you perform confidently in the competition ahead. Keep practicing, stay curious, and continue exploring what you have learned. We're excited to see your creativity, problem solving abilities, and teamwork come to life during the competition. Thank you for your enthusiasm and participation. We wish you all the very best, and we look forward to meeting you again at the MazeX 1.0 competition. Thank you.